All right, guys, let's do number 48. Beautiful. An astronaut on the surface of the moon fires a cannon to launch an experimental package, relieves the barrel, moving horizontally. What must the muzzle speed of the package so that it travels completely around the moon and returns to its original location? All right, so what is going on? So you have a cannon that's going to fire and it's going to go around the moon. And it's going to return at that point. So the question is for part A is what must the muzzle speed of the package so that it travels completely around the moon? Before we start, folks, let's find the radius of the moon. Let's just call that big R, the radius of the moon. So the radius of the moon is going to be 1738 kilometers. Beautiful. And the force of gravity from the moon is going to be 1.62 meters per second square. So anyways, what must be the centripetal acceleration? Well, don't we know that the centripetal acceleration is really just v squared over r? So, and it's asking for the speed, so it's really just the square root of gr. So it's just g and the r, which I already have that stored, gr. So once you calculate that, the centripetal acceleration, or I mean the velocity is 1.67 or 68 kilometers per second. So that's the speed that I would have to travel. I rounded a little up actually. So it has to travel faster than that for it to go around the moon. So how long does the trip take for this cannonball to go around the moon? So assuming the free fall acceleration of the moon is 1/6 of that of the Earth. Oh, I didn't read that part. Whatever. Somewhere around there. Maybe the calculator. Maybe you guys might have a tiny bit of a different answer, but it doesn't really matter. So anyways, let's calculate this. So let's take the whole circumference of the moon, 2 pi r, and divide it by the speed to get the time, all right? That's straightforward. So let's get that. I'm going to put 2 pi r in my calculator. 2 pi, I already have everything stored, divided by the speed. Let me see if I stored the v. Looks like I did. I think I did. Yeah, I did. Okay, so there we go. So the time it takes here, what I got is going to be 6,508 seconds. So I'm going to divide it by the 60 square. I'm going to convert that to an hour. So that's approximately 2 hours. Or 1 hour and... So it's going to be 1 hour, 1.8 of an hour. All right, folks. I hope you enjoyed. This is going to be the... All right, we're done.